Morning all. Welcome back to Samvaad. So today we have the fourth talk of the theme, namely 5G verticals and rollout. And today we have Dr. Sanket Kalamkar from all the way from Qualcomm San Diego, and he'll be speaking about beam management in 5G, stochastic geometry analysis. And Professor Vinod Reddy is the session chair for today's talk. He's currently an assistant professor here at IIIT-Bangalore. He received his PhD from NTU Singapore and has been working in the industry for several years before joining IIIT. And his research interests lie in the areas of radar design and processing, and also biomedical engineering. So without further delay, let me hand over the stage to Professor Vinod so that he'll introduce the speaker.
Thank you, Nikhil. On behalf of Samvaad team, and it's my privilege to introduce Dr. Sanket to our Samvaad audience. Okay. Dr. Samvaad S. Kalamkar received his BTech engineer degree from the College of Engineering, Pune, and PhD degree from the Electrical Engineering from the Indian Institute of Technology, Kanpur, India. He is currently working as a systems staff engineer with Qualcomm Technologies, San Diego. And before that, he was a researcher at INRIA, Paris, a Simons postdoctoral fellow with the University of Texas at Austin, USA, and a postdoctoral research associate with the University of Notre Dame, Indiana, US. His research interests include wireless communications, spectrum sharing, vehicular networks, XR over wireless, and green communications. He has also received the Tata Consultancy Services Research Fellowship and Dhirubhai Ambani Scholarship. He has also received the Best Paper Award at IEEE Globecom 2020. A wonderful accomplishment indeed, right? So, coming to this topic of today's talk, Dr. Sanket conceives the idea of a system level model for beam management. As I understand, this work discusses pretty much all the modules of end-to-end communication in the context of 5G new radio. The advantage of this holistic approach is that the model yields analytical expression for beam management aspects, such as the number of beams per cell per mobile terminal under variety of network scenarios. Okay. Service providers of 5G network will be immensely benefited with this clarity on the development, with the clarity on the deployment, resource sharing, operational overheads and cost. I mean, this is a very, very important aspect because 5G is now kicking on and moving towards implementation, right? In the interest of eagerly awaiting participants who want to learn more about beam management approach from the inventor, I invite Dr. Sanket to deliver this talk. Dr. Sanket, over to you.
Sure. Yeah, thank you, Professor Vinod, for the nice introduction and giving the very nice summary of the talk. Indeed, what you said is the kind of the focus of this talk. And also, I would like to thank the Samvaad team for inviting to give this talk. I'm very happy to share my thoughts on beam management and related development. So let me share the screen, the presentation here. Okay, so this is the work done kind of a couple of years back, but it's still quite, there are a lot of area to do research in this. So in this area, that's why I would like to still focus on this beam management in 5G. Usually, in addition to talking to beam management aspects of 5G and the challenges associated with it, I would like to also introduce a mathematical tool which uses these tools from the stochastic geometry, especially the point process theory from the mathematics. And then how we can use these tools to have a kind of an analytical, to get the analytical expressions for this beam management aspect and get crisp insights into the study of the beam. So this work was done when I was at INRIA in Paris with my supervisor Francois Baccelli, and then it also was a collaboration with the Nokia Bell Labs in Paris. So these were the researchers from Nokia Bell Labs. Indeed, the Nokia Bell Labs was the one who brought this problem of beam management to us to get some analytical insight. So I will talk about that more, about the motivation and why this analytical approach towards beam management is useful. Okay. So this is a brief outline for my talk. I will first give the basic introduction of stochastic geometry and also motivate and then highlight the challenges for the beam management problem. Then we'll talk about how stochastic geometry tools can be used to answer or analyze the different aspects of the beam management. Then I'll give some conclusion and outlook, like what could also be done in the future in the area of beam management. So let us talk about why stochastic geometry, or what is stochastic geometry. So let's focus on this first figure on the left-hand side. So these circles essentially denote the position of these various wireless nodes. They could be the base station, they could be the vehicular communication, vehicles in the vehicular communication. This could be mobile terminal like cell phone or iPad or whatever. And let's assume that so these blue dots here denotes this interfering node for this transmission going on between this green and red node. Now, obviously, one can, for this given set of coordinates, one can do the analysis in wireless communication, such as calculation of the success probability or the outage probability or the throughput or the ergodic capacity and so on. But obviously, you can do using these typical wireless methods, but obviously then after sometimes the nodes move around and then you probably see a new realization. And then obviously now since the locations have changed, the network topology has changed, then you have to redo all the calculations again, and so on in this field. So in my opinion, I do not see these three figures as three different networks. Instead, I see these figures as a realization of a network, three different realization of a network, or the ensemble of a network. Now, the challenges with what happens is that if we focus on just a specific realization, the analysis doing for a specific realization is not very useful, meaning that you have to keep redoing all the calculation again and again as the topology of the network changes. And now, then how to characterize the performance of such a network? So it's essentially because the nodes might move randomly or the locations are usually unknown. So it is helpful if we can make some statistical statements about this class of network realization or the ensemble of network realization. And once we do this statistical analysis, we can obtain the spatial averages, meaning that as the averages over the nodes spread across the space. Okay, and then that gives us the expected values or the average values of certain performance metrics. And that is where the stochastic geometry comes into picture when it comes to the analysis of this network. So we can take an example. If you are in Bangalore, you have a different street geometry, buildings and the node topology. Now, if you move to Hyderabad, you will see entire different network of nodes. If you want to do the analysis, it is very difficult to do the analysis for each different city or each different location, right? So that's why we need a statistical statement to talk about this network realization. Now, what is Poisson point process? So stochastic geometry is a sub-area of point process theory. One of these key or important point process is this Poisson point process. So essentially what happens, these network nodes, whether base station or mobile phones or the vehiculars, can be modeled as points in some space. In this case, it is a two-dimensional space, or it could be 3D. If you have drones and everything, we can model these locations of these nodes in 3D. Okay. So one of the popular point process is the Poisson point process, or PPP, because the analysis is tractable for the PPP, or there are other processes where you can have these cluster of the points and so on, but I will not talk about those point processes in this. So the homogeneous Poisson point process can be characterized by a single parameter called lambda, which is the intensity. That means the number of nodes per unit area in the case of 2D. And then the number of points in the disjoint areas are independent. For example, the number of points or the nodes in area A and the number of nodes in area B, these numbers are independent. And the number of points in a region, let's say in a region A, is Poisson distributed, meaning that the probability that there are a number of nodes is given by this Poisson, very well-known Poisson formula. And in modulus of A, it denotes the volume of region A, which is the area in two dimensions. Okay. Now, obviously, it is the first question comes to the mind. Okay, this is some mathematical model Poisson point process, but how accurate it is, means how accurately it characterizes the location of different nodes. For example, let's talk about that. This is the actual deployment of base stations in London. So these are on the scale of meters, and then this is the distribution, or you can say distribution of the base stations in London. Now let's take up a simulated Poisson point process with some intensity, and this is how this Poisson point process looks like on the same scale. So we can see that there is from the visual perception, we can see that there is some similarity in characterizing the locations of the nodes. So it has been indeed shown that the stochastic geometry can lead to the analysis that is reasonable fit with the real deployment as shown in this figure. And also it leads to some simple analytical expression for several performance metrics, such as the throughput, outage probability, and so on. And the most importantly, it allows system level performance evaluation. So you have different aspects of the systems which can be taken into account. So I will show later in the talk where how the system level analysis can be done using this. Now in this talk, we will obviously, the stochastic geometry can be applied to a variety set of problems, vehicular communication, spectrum sharing, base station 5G and RLT, or side link communication, and so on. But in this talk, we will talk mostly about the 5G beam management problem, because the beam management is central to 5G NR. So if time, the focus will be on this first part, where we will use the tools from stochastic geometry to analyze the beam management problem. And if time permits, I will show the reverse process, like how the practical problems in beam management can also lead to the development of fundamental mathematical tools in point process theory. So if you are interested, there are some papers which are already published with my advisor, François Bachel. So in the first, this one was published in IIIT Transactional Wireless Communications, so while the second one was more on mathematical aspects, so which were, and this work was published in journals of probability. Now, the first question, like, okay, what is the motivation for the beam management? Otherwise, like, the problem should be interesting in order to do some research. Let's motivate the beam management. We know that the traditional cellular networks, such as the 3G and 4G, the base stations have single beam from each panel, meaning that they transmit omnidirectionally. So for example, there is a base station at this point and it is divided in 3 sectors. And then there is only one beam covering this entire region in the cellular network. Okay, and then the user equipment, which could be the mobiles or the vehicles, they are also omnidirectional, meaning that they can receive from all directions. The key concern in this traditional network was this intercell mobility, meaning that if the user is moving on this straight line here, these are the cell boundaries, and then at these cell boundaries, the control transfer will be done from this base station to this base station at this point. Now there is a handover from, essentially this process is called handover, where there is a transfer of the communication from this base station to this base station here. But what could happen due to this transfer? There could be a radio link failure and interruption in the cellular communication. Now, what is different in 5G NR? So this figure shows the typical scenario in 5G NR. So the intercell mobility remains still the same. But now what happens in the intracell? If we focus on this hexagon here, we can see these red beams inside this cell. So as the user moves, so the beams, in 5G, essentially the beams is the integral part, meaning that if the user is lying here, the user will be served by this beam. if the user moves to this beam, then the user will be served by this beam. Now, in addition to the intercell mobility, now one also has to focus on the intracell mobility and the beam selection within when it transfers from one base station to the another base station at this cell boundary, and also the beam reselection when the user is within the cell itself. So as the user moves from this beam to this beam, then the new beam that will be used to transmit to the, or that receive from the user will change. So essentially, this beam can be generated using multiple antennas. So you can have multiple antennas at the transmitter, which could be the base station or the user, and also at the receiver. Okay, and then you can obviously how these beams are generated is connected to the signal processing done at this transmitter and the receiver using this multiple. Now, so the key difference here between the 4G and 5G NR is these beams that serve the user within this when the user is inside the cell. And there is a intracell mobility that we have to consider in addition to the intercell. Now, obviously, the challenge is that what are the challenges with this is that it may be possible that since the user is moving, if let's say you are in a very fast and Rajdhani Express and the user is moving very fast, then there will be frequent beam switching within the inside the cell, and also the frequent handover between these two base stations. And then due to which there will be a frequent communication interruption between the base station and the user, which we want to minimize. So the challenge is that, there is a trade-off as this figure shows. So this is a transmitter and this is a receiver, and there are different beams. If the beams are very highly directional, meaning that this user will receive only signal from this transmitter, and since this transmitter is transmitting only this specific direction, this receiver will experience interference only from this direction and not from the other direction. So essentially, the beamforming helps to improve the signal quality, and at the same time, it reduces the interference. But obviously, this beamforming should be robust to the mobility condition, as I said earlier. If you are in a Rajdhani Express and then you are moving too fast, so there will be a lot of beam switching from one beam to another beam, and that leads to the communication interruption. And also, we have to tackle the all set of users like pedestrian or the vehicular speeds and so on. And the key thing here is that to avoid the delay is to discover and quickly switch the beams between these set of the beams here. Now, there are three key challenges in the beam management. One is the beam selection, which means to search for an appropriate beam with the new base station. And because it is important, and this beam selection process is affected by the handover process because it leads to this base station handover overhead. And so overhead meaning that there is an interruption in the communication between the base station and the user. And the beam reselection, as the UE switches the beam from one beam to another beam when it is moving inside the cell. Right? Again, there is some interrupted communication. And then obviously there is a possibility that the best beam is not found, and then there is due to the fading or the poor communication channels, there is a beam failure, and then one has to recover the beam again. So these overheads or this communication interruption due to this base station overhead and the beam reselection overhead, this overheads reduces the time that is available for the data transmissions. And then that essentially reduces the data rate or the throughput of the user that achieving this. Now, I hope I could motivate the management problem in the cellular case. Like if you have any question, just please stop me anytime. Now, the second follow-up question.
Sanket, can I ask you a question?
Yeah, sure. Yeah, please.
So this beam selection, is it relevant only with the millimeter wave band like 26, 28 gigahertz or above, or does it hold good for lower frequency bands? For example, 600, 700, 800, and so on.
Oh yeah, that's a good question. Indeed, means technically there is no challenge in such like to use the beamforming even at lower frequency. I don't know about 700 and 800 megahertz, but if we go to sub 6 gigahertz frequencies, which is also this 5G is going to use, it is possible to use the beamforming. So as I will show the numerical results, we did the analysis for both sub-6 and this millimeter. But this beam forming or the beam management problem is more challenging for mmWave or more interesting for mmWave due to the reason is that in mmWave we have very high attenuation, right? And then it seems that how things will work is that mostly the beams will be used at the millimeter wave because we want to minimize the interference because already this radio attenuation is very high at millimeter. So this beamforming helps in that case. Even if it helps in the sub-6 case, but I think the main motivation for sub-6 in 5G is to have the coverage, meaning that the users which lie at the end of the cell, we would like to serve those users. So still we can use the beam forming in sub-6, so there is nothing stopping for us like to use the beam management in sub-6. So it can be done for both.
Thank you.
And obviously, now the question is that, okay, we can use beams in 5G, but why is this problem hard? Why should one focus on beam management, right? Now, the key challenge is like, obviously one can do the system level analysis. You get big computers or the servers and you do the simulation, you put nodes. And then, as I said, you're in Bangalore and you are in some area, and then like a Silk Road where Silk Board, and where there is crowds, and then you do the analysis. But you move to some outer side of the Bangalore, let's say to IIIT, and then you do the analysis. So you have to keep doing that analysis again and again. And then in the system level analysis, we have the typical wireless challenges like frequency, what should be the antenna configuration, how is the channel propagation, also the physical layer, how are the wireless links, what coding techniques to use, also the network geometry, and then the interference is different, how to share the resources, how to sense signal, and then do the mobility management for mobile users. And obviously, then we have the challenges associated with the beam management, as I said earlier, beam tracking, beam selection, beam switching. And obviously, this propagation is highly sensitive to environment, especially in the millimeter wave, such as even if you move the hand, if there is a passing vehicle, those millimeter wave signal can get blocked. So the blocking is another big issue in beam memory. And also we have the different network scenario, like we have a mix of omnidirectional or directional users, like let's say people using 4G network, people using 5G network, then the mix of user speeds, pedestrians, bikes and cars, mix of geometries, some cells are bigger, some cells are smaller depending on the density of the users, or the users are closer to the serving base station or they lie very far from the serving base station. And obviously it's a mix of the fading and the blockages present in the system. Now, if we combine all these parameters, like these are the only some set of the aspect, system level aspect that one has to consider, but there are many more in, like if you go into details. And if it comes to the system level analysis, then like tuning all these parameters becomes an headache, right? So the goal is here that if there is something that we can do using analysis and get some tractable analysis so that we can simply select those parameters and see how the performance changes. Obviously, it cannot replace the system level simulations because those are more reliable and more realistic, but this tractable analysis can give us some insights that can help us to start the simulations, rather than it can narrow down the amount of the number of simulations or the system level simulation that one has to do. Right. Now again, so as I said earlier, this problem was brought to us by Nokia Bell Labs when I was I was a researcher in Paris, and then they were doing the system level simulation, and what they found that the system level simulation indeed take a few days, even at the industry level. Right, and so they wanted to have some quick insights into how this beam management work, and that's how this this work kind of born. Then the question is that how can one solve it, right? And now I have introduced the stochastic geometry, I have motivated the beam management, but how can one solve this, or what is the achievement out of this? Now let me give some summary of contribution. So this is the first mathematical optimization framework for the beam management. So there was no analysis earlier in the case of this mathematics for the beam management. where we calculated the optimal number of beams that maximizes the area spectral efficiency. Essentially, area spectral efficiency means the throughput one we can, it's a kind of it characterizes the throughput that user can get or the data rate that user can. And then it allows the stochastic geometry allows the system level analysis, meaning while taking into different aspects, such as the average speed of the mix of mobile terminals, pedestrian, bikes, and cars, and also the beam management error. Like as the user is moving, the user might be connected to the suboptimal beam, not the optimal beam. Then that we call beam misalignment. And also the beam selection and reselection overheads when the user moves within the cell and across the cells. And then we find the number of beams that provides the best spatial average rate for the mobile terminals for all types in a large box. So as I said earlier, the stochastic geometry usually gives you the average performance of different performance metrics. So we focus on this average rate. And we show that this tool can give us the fast numerical result to evaluate this 5G new radio compliant radio access network. So it's not only related to the 5G NR, although the focus is only on 5G NR in this talk, but this analysis can be applied also different beam-centric systems such as IEEE 802.11ax or Wi-Fi 6. And in the process that not the goal of this work is not to only analyze the beam management while analyzing, because this was the first work in this area. Then we also define and evaluate many new and fundamental performance metrics, such as the intensity of beam reselection, and then the time of stay, like how long the user stay within the beam, and then what is the probability of beam switch, meaning that because this directly affects the overheads. Now let me come to the more technical part of the talk. So just a caveat that even though there will be some mathematical equation, I do not those equations are just to show that how stochastic geometry is useful, and then how can the analysis be done for using stochastic geometry. Now this is the network model for the typical 5G NR. So these triangles here shows the base stations. And then there is a mobile terminal shown by this red square, and this mobile terminal is moving on a straight line for simplicity. And so this is the trajectory, this green dotted line. Now we assume that this mobile terminal is served by the nearest base station, which is kind of intuitively makes sense, but in practice it could connect also to a base station which is farther. But in this work we'll focus that this mobile terminal connects to this nearest base station. And these base stations are located or follow this homogeneous Poisson point process in 2 dimensions with intensity lambda, meaning that there are lambda number of base stations per unit area. Now, when we say that when this mobile terminal connects to this nearest base station, it forms a Poisson-Voronoi tessellation, meaning that this solid line shows the cell boundaries, that if the user lies within this cell, then it will be served by this user. If the user lies here, then it will be served by this user. When there is a communication happening between this base station and the user, the rest of the base stations could act as interfering base stations, okay? Because they are also serving their own users. And then the another assumption is that as of now is that this base station serves only one user per time per resource. So this work has been extended in another work for when this base station serves multiple users within the same resource flow. So for now, for the simplicity of understanding of this problem, we'll focus that only one user is served by this base station. Now coming to the beamforming model, we assume that each base station has n beams shown here, and there is serving a mobile terminal. Now we approximate these beams as a sectors, meaning that if you have so this red solid lines show the actual beam pattern. So this is the main lobe of the beam, and these are the side lobe of the beam. Then what we can approximate this main lobe of the beam by a sector or the triangle as shown here. And this width of the triangle is this beam width shown by this verb phi n, which is dependent on the number of beams. So 2 pi is the 2 pi over n is the beam width of it. And within this main lobe of the beam, which we call also the both side direction, the antenna gain is denoted by Gn. So this is the main lobe, and n is the number of antennas. And in the side lobe gain is characterized by the GSN. So this one can have, depending on how is the multiple antenna structure and the signal processing techniques used, one can have a different expression of GMN for depending on the number of, as a function of this number of gains. Okay, so there is no specific assumption on this what can be a value of this or expression for this main lobe gain and the side. Okay. So to summarize that, so within the main lobe, the gain is GMN, and in the side lobe, it is GSN. This is an example. If we say that we have 4 beams, this is a one cell of this base station. Now, so there are 4 beams in a sectorized model for these 4 beams. So if the user lies in this area, it will be served by this beam, and so on. Okay. Now, certainly, as I was saying earlier, that blockage is a key impediment in mmWave. So what does it mean by blocking? So there is a base station here, and there is a mobile terminal here. And let's say there is a building here. Now, and this user is served by this base station, but now this beam is blocked by this building here. So we call this path as a 9 line of sight path. And also there might be, and this is a line of sight path, meaning that there is no blockage between a base station and this mobile terminal. So there is a direct path of communication. So there are several models models for characterizing the blocking. But in this talk, we will focus on a simple model, which is a LOS wall model, where it means that the base stations have a line of sight to the user as long as the distance between the serving base station and the mobile terminal is smaller than RC. So this is a ball of radius RC. And then whatever base station that lie within this ball of radius RC from this MT will have a line of sight communication to the mobile terminal. The users, the base station that lie outside this ball, they have a line of sight, a non-line of sight communication to the user. So in this case, this base station is an interfering base station, but it has a non-line of sight transmission to the mobile terminal. While this base station is still an interfering base station because this is farther than this serving base station, and it has no line of sight communication to the mobile terminal. So this is the line of sight ball model for the modeling, for the characterizing blockage. We assume that there is a channel, fading channel denoted by HX, the channel power gain, from the base station located at some location X, and this X is essentially a coordinate to the typical mobile user. Okay. For the analysis, we assume relay fading with unit power again, but this analysis can be extended to the Nakagami fading and other fading as well. And I will show in the simulations numerical results that even for the trends that we observe for the relay fading are exactly the same also for the Nakagami fading. So this model, although the analysis becomes very complex for the Nakagami fading model, but the relay fading model is good enough to gain or to see the trends in the beam management, how the different aspects of the beam management affect the performance of the user. Now, obviously, when we have the beam, the key challenge is this beam misalignment. Now, what happens is beam misalignment is that in practice, if you go through this 5GNR standards, this beam selection or reselection, these beam measurements, essentially what beam is the best beam for the user, happens every a certain period of time. It could be 5 milliseconds, 10 milliseconds, or 20 milliseconds. Now, what could happen? Let's say these crosses show the location at which the beam measurement is done, or the beam, whether the base station asks the user to report which beam is the best beam to communicate over. So this crosses denote the location. Let's say this could be a 20 millisecond difference between these 2 points. But what could happen at this point, the beam measurement is done and the beam is selected, and this red beam is the best beam at the time t. But obviously the user is moving, and then if the user is moving very fast, then it could be possible that before another beam measurement is done, the user has already moved to a new beam, right, in the area of the new beam, let's say this blue beam. But what could happen, since measurement is only done at this point, even the user is now at this point at T dash point, the user is served by now this side lobe by this red beam. Now, obviously the side lobe gain is smaller than the main lobe gain, which reduces the signal quality to the user due to this beam misalignment. Now, certainly, now we can characterize this beam misalignment using statistically, because this is quite a random scenario depending on the direction of the user, in which direction the user is moving and so on. Then we can have a probabilistic model to characterize the beam misalignment, meaning that with probability 1 minus PBM, the user is served by the best beam at a given time, and then with probability PBM, which is the probability of beam misalignment, the user is served by GSM. So I will not talk about it. So there are different models to compute this probability of beam misalignment, but if you want, you can refer the paper how to calculate this probability of beam misalignment. But this is how, but this PBM can be computed in different ways depending on what are the system assumption, what is the network structure or the topology, and based on. Now, in nutshell, the system model looks like this. We have a different cells, base station denoted by the triangles. There is a mobile user which is moving on this straight line here. Now, as the mobile user moves on this straight line, there is a base station handles, as I talked earlier. So these solid lines, black lines show these cell boundaries, and this yellow circle here shows the base station handle location. And this brown circle shows the beam reselection locations when the user moves within the cell. Meaning that the user is moving, so at this point, there will be beam switching from this beam to this beam. And then at this point, there will be beam switching from this point to this point, right? And this base station, again, as I said earlier, these base stations are deployed according to the Poisson point process. And this dashed pink color shows the different beam boundaries. So this is a snapshot of this Poisson cellular network. I call this Poisson cellular network because these base stations are deployed according to the Poisson point process. Okay. Any question at this point? Okay. Now let's come to some analysis for the given model.
Sanket, there is one clarification on this. So this Poisson point process for creating the cell boundaries, does it depend upon the number of beams that the base station has?
No, it actually what happens, this cell boundary is dependent on the number of base station per unit area. Now, if you increase the intensity of these base stations, like meaning that the number of base stations per unit area, if you're in a crowded area, let's say siltboard, it makes sense to have more base station to serve more users, right? Now, in that case, the cell boundaries will shrink, they will become smaller because these base stations here, they are coming closer and closer, right? Now, if you go to rural area, then this base station will be much farther apart from each other, and then the cells will be larger. But now what happens, it's actually the other way around. Since the cells are larger, then if we have 8 beams, then each beam is covering a larger area of this cell. Now, if we have this cell, smaller cell, then each beam is covering a smaller area, right? So it's actually the other way around. It depends on what is the intensity of the base station or the number of base station per unit area that determines how large area a beam can serve. Okay. So we can have the number of beams, like it could be 16, it could be 32. So it depends on the operator and who is deploying the network, depending on what is the multiple antenna configuration and signal processing capabilities.
Okay. Just Sanket, sorry to interrupt. Just one more thing. This cell area should also be dependent on in which regime you are operating, maybe in sub-6 gigahertz or mmWave. Is it depending on that also? Hello?
Which one? No,
so the cell area, I'm asking the cell area, is it depending on that whether we are operating sub-6 gigahertz or in millimeter wave regime?
Yes, exactly. Yeah. So I will also show in the numerical results. So it depends actually on the millimeter of which frequency you are operating, because it has to do with the propagation characteristic like attenuation. Essentially, the millimeter wave, the cell areas will be smaller compared to the sub-6 because the attenuation is larger. Especially because the user that will lie on these cell boundaries here, they will not be served well if we have a large cell area for MM. So essentially, the small cell networks, it is expected that they will be deployed in millimeter wave, and this macro cell will still be deployed in sub-6 area. So that's a, yeah, that's a good point. Yeah.
Thank you. Thank you.
Okay, now as just again clarification, even though there are equations, it's just to give some intuition. One need not focus on this equation and understand this equation fully to understand the impact of stochastic geometry on beam management. So essentially, we are focusing on so there are two important aspects in the signal communication. One is the signal strength and also the interference. So one has to calculate the interference. Assuming that we remember that this where phi n denote this beam, this is the beam width of this main lobe, and then there is a gain GMN in this area, in the inside lobe gain is GSN. So since we have 2 pi over to cover the all area, then there probabilistically the user might be lying anywhere in this area, right? So we don't know which direction the user is lying. And then using the probability, we know that the user will be served by the main lobe with this probability over phi n over 2 pi, and with the side lobe with probability 1 minus over pi over 2 pi. So this is due to that the beams of all base stations are oriented towards their respective mobile terminals, which are lying uniformly randomly direction. Right? So the antenna gain of the interfering base station to the user will be given by this expression. Okay, so Gn is the interfering base station gain with this problem. And then we can calculate the interference power by a base station located at location X, and sum over all the base station to calculate the interference power at the user, which is given by this expression. So we essentially have to sum over all the interference power, and P is the transmit power of a base station, and Gn is the antenna gain, and Hx is the fading power gain, and L is the path loss model. What it could be anything. And then we have the signal to interference noise ratio, SNR. So the numerator is the signal power from the serving base station. So this is the serving base station gain, antenna gain, and this is the fading. And there is the noise power and then the interference power. So we have the SNR calculation. Okay. And again, this noise power depending on what bandwidth we have, whether we are operating in sub-6 or usually the bandwidth in sub-6 could be smaller than mmWave. So usually in sub-6 they go for 20 megahertz, and in mmWave there is a possibility of going to 100 megahertz. Now essentially this SNR is crucial to compute a different performance metrics. One is the success probability, which is nothing but the outage probability. This is probability of that SNR is greater than some ratio. So 1 minus success probability is nothing but this outage probability. And how it is calculated in stochastic geometry, it is essentially a spatial average, meaning that the fraction of the mobile terminals in a realization that can have SINR larger than beta, meaning that you generate a realization, you have multiple users, and you see what fraction of the users have SINR greater than beta. That gives us the success probability. Now, using this obviously success probability, one can also calculate this ergodic Shannon rate given by this famous formula, where log. So this E is the expectation, and we calculate the log of 1 plus SI. So Qmax is the maximum limit on this SINR can be achieved in practice due to this RF imperfections and the modulation encoding. Now, essentially, this ergodic Shannon rate also can be written in terms of this success. So even if you want to calculate ergodic Shannon rate, it is sufficient to compute this success probability. So we'll focus only on success probability. Now, let's say this expression gives the analytical expression for the success probability. So this will be a big expression, but I will show how we can decompose this equation to get insight. So there are two main parts of this equation. One, the success probability when there is no beam misalignment, which happens with the probability 1 minus PBO, and QS is the corresponding success probability, which depends on the number of beams, SINR threshold, and the main lobe gain. And also when there is a success probability when beam misalignment. So this is a simple probability formula. Now this expression shows this individual terms of this QS. So this is again the model. Remember that this mobile user will be served by this serving base station, and there will be base stations, interfering base station, which could be an LOS or which could be having LOS communication to this mobile. Okay. So essentially, it shows that this base station will cause interference with the main lobe if it pointing its main lobe towards this mobile terminal. And then probably this base station is pointing its beam to its own user. So this base station will cause interference to this mobile terminal in side lobes. Okay. Now, what this term shows, so in this expression, this first term here shows that what is the signal strength of this LOS serving base station, essentially this one. So since we have this LOS ball model, the integration goes from 0 to RC. And then the second term here shows that if this serving base station lies outside this LOS ball, then this is what will be the signal strength or the success probability due to the if the serving base station is outside this LOS ball. Now these are the noise terms in both cases. And this is the main lobe interference, whether the interference is coming from the main lobe or the side lobe. And then these are the interference terms coming from the LOS base station that are LOS, communication to the user, and this term comes from the interference due to this LOS base station. So even though this in the first view, this expression looks very complicated, but we can see that we can factor this expression into multiple areas or different aspects of this communication for beam management that takes into account beam misalignment, also this blockages, LOS or NLOS base station, noise, interference, whether that interference is coming from the main lobe or the side lobe, and so on. And this is a very general expression. So for some specific parameters, for example, if you set this path loss exponent alpha to 4, you can even calculate this expression in closed form. Okay. So although this expression looks very daunting, it's very simple expression and it gives insights. It allows you to see how each factor or each aspect of this beam management affect this success probability. Yeah, and then now I have talked about the SINR, but now the key question is the mobility. I told earlier that as the user is moving, there will be beam reselection and beam selection, right? As shown here, as the user is moving within the cell, as it crosses these beam boundaries, there will be a beam reselection, beam switching from this beam to this beam. Now, it is important how frequently this beam reselection happens. If this beam reselection happens, so the intuitive logic is this, like if we want to have beams this narrow because it increases the signal strength, but if we make these beams narrow, then this beam switching will happen more frequently and there will be more frequent communication interruption from the base station to the mobile terminal. So it is important to calculate what is the average number of beam reselection per unit distance, which can be modeled as another point process. So you characterize this crossing as a point, which leads to another point process. And we can use some tools from the stochastic geometry, such as the Campbell's theorem. I will not go into that, to calculate what is the average number of beam reselections per unit distance. If you do the analysis, suppose there are n beams per base station and there are lambda base stations per unit area, the number of beam reselection that will happen per unit distance for a speed v, if the user is moving at speed v, is given by this simple expression. So we can see that this can be modeled by a very simple expression. And this is very intuitive. If we increase the number of beams, the area covered by each beam will be smaller. So the number of beam reselections will increase. So this is proportional to the number of beams. Now also to the number of base stations per unit area. If the network becomes dense, meaning that this lambda increases, obviously the cell size will become smaller and then each beam will cover a smaller area. Then since each beam will cover a smaller area, again, that will lead to a higher number of beam reselection. So this makes sense. And then if you want to calculate the number of beam reselection per unit time, then we have to simply multiply by this speed v. That gives the number of beam reselections per unit time. And then another aspect is the base station handover location, as shown here. If the user is moving from this cell to this cell, this yellow circle shows the handover between from this cell to this cell. Now, this is a very well-known result in stochastic geometry, and is given this intensity for this, or the average number of the cell boundary crossing is given by this expression. So it solely depends on the intensity or the how dense the network is, meaning that if you increase again lambda, which is the density of base stations per unit area, then these cell sizes will be smaller and the user will be moving between two cells quite frequently, because as you increase lambda, this cell area will be smaller and then this distance will be smaller, and for a given speed, there will be higher number of crossings per unit area, per unit time. And then again, the time intensity, meaning that the number of base station handover per unit time is given by this formula. There we have to simply multiply by the speed to this formula. So this is a very old result, proved in 1997. It has been 25 years. Now, essentially, now the second aspect is the time overhead, which is related to the beam management. Now, what we saw, there are two aspects. The one is the beam selection. After each base station handover, there will be periodic beam measurement, receiver processing time, handover interruption. And then there is a beam reselection time due to this periodic beam measurement and the receiver processing time. And then the total average overhead per unit time will be given by this simple probability formula. So in this case, mu b denotes the probability that there will be intensity of delay, how frequently this base station handover happens, and with each base station handover, TB amount of time is used. So there is a communication interruption of TB amount of time. Similarly for the cell crossing here, like mu c and TC. Then essentially, finally, we can calculate the area spectral efficiency, which is the density of the base station times this periodic Shannon rate, multiplied by this time available for the data transmission. So TO here is the total overhead or the communication interruption. So obviously per unit time, the time that is available for the data interruption is 1 minus T. So plus denote that it is the maximum of 0, because the time cannot be negative in this case. So this shows that this is the time available for the data transmission. And ultimately the final optimization problem is this one, where we want to maximize this effective area spectral efficiency, and we want for a given number of beams. So we want to calculate the optimal number of beams such that this effective area spectral efficiency is maximum. Now this is a one-dimensional problem. You can simply do a scan over different multiple antennas, like going from 1, 2, 3, 4, 5, 6, or different number of beams, and see for which value we get the maximum effective area spectral efficiency. So this is not a very hard optimization. These are the system parameters. So FR1 says that sub-6 frequency is 3.5 gigahertz, and FR2 is the millimeter wave, whereas it is 26 gigahertz. And the bandwidth is 100 megahertz and 400 megahertz. And then we can see, so these numbers were obtained by the Nokia Bell Labs through their experiments, field experiments. So each beam handover leads to about 23 milliseconds of communication interruption. While the cell handover, meaning that from transfer from one base station to another base station, there is a larger communication interruption, which is about 43 milliseconds. And this SSB periodicity, meaning that how frequently the beam is reselected, it is 20 milliseconds. And we consider different mobile user speed, like 330 and 120 kilometer per sub-6 and 330 kilometer per mmWave, right? And as Prem said earlier, that it affects also different intersite distances, means what is the coverage, essentially what is the average cell area of in each case. So in FR1, obviously the cell area is larger, 250, 500 or 100,000 meter. In FR2, it is smaller. And then there is a blockage model, as I said earlier, and then path loss exponent. We use these ways. And this is the one result I would like to highlight. So it gives a lot of information for this one figure. Essentially, what we do here, we plot this effective area spectral efficiency on y-axis and the number of beams on the x-axis. Actually, the number of beams here, it is 2 to the n, just because we do the analysis from one beam to up to, like you can keep going up to like 1024 beams in practice and so on. And we do it for different intersite distances, meaning that what is the average distance between the base station? It is 75, 120, and 250 meters. So this is for mmWave analysis. And then we consider two speeds, which is the 33 kilometer, which is the pedestrian speed, and the solid line is the 30 kilometer per hour, which could be a vehicle speed. Now this is for the railway, but the same trends hold for the Nakagami. Now what could happen as the number of beams increases here, we see that initially the effective area spectral efficiency increases and then it starts. So there exists an optimal number of beams. Why do we see this trend is that initially when the number of beams are smaller, the beam forming gain is smaller because the beams are larger. So there will be a smaller, the energy is concentrated over a larger area. So, and then the desired signal intensity is smaller. Also the interference will be larger. And so as we increase the number of beams, the beam area becomes smaller, and then we start getting the beam forming gain, and the effective area spectral efficiency increases. But at certain point, what happens if the beams become too narrow? Because remember that this is per cell, right? Per cell. Then if you increase the beams too much, then each beam is covering very small area, narrow area. Then for a given speed, there will be a very frequent beam reselection and very frequent communication interruption. And due to which the time available for the data transmission reduces, and then effective area spectral efficiency starts. And at some point, it goes to zero. Okay. Now, certainly when the solid line, the area which is the 30 kilometer per hour, the effective area spectral efficiency is smaller because users are moving faster than this 3 kilometer per hour. And so there is a more frequent beam reselection happening. And so that leads to more frequent communication interruption, reducing this effective area spectral efficiency. Obviously, due to the same reason, the optimal number of beams for at 30 kilometer per hour is smaller than the optimal number of beams for 3 kilometer per hour. Now, also there is a trade-off as how the network is dense. So 75 meter meaning that the network is denser than the case ISD of 250 meter. So initially we see that for ISD, so this result is helpful how much one can densify the network for a given set of parameters. So initially when the number of beams are smaller, the denser network is good because there will be not many beam reselection and beam reselections. But as we increase the number of beams, for a smaller network, the denser networks, meaning that the cell areas are smaller, there will be more interruption communication, and the area spectral efficiency reduces at this point. So same things with this case where we can see this yellow curve falls below a red curve at some point, right? Because of the same phenomenon.
Sanket?
So this is, yes, please.
Just a quick question. So is this 3.3 gigahertz or 26 gigahertz? Because I assume that
this is 28 gigahertz. 28, yeah.
This is for?
Yes, that's correct. This is a millimeter wave. This is for 28
This is a millimeter
gigahertz.
wave. So I am assuming that for 3.3, if you do it, then the whole thing will probably shift towards the right. Is it?
Yeah, that's a good question. Yeah, actually, it depends again the model that we have assumed. Also, it highly depend on the intersite distance, but in general, that is true. It will move towards the right. The number of optimal beams we can have, because the cell area will be larger in sub-6, 3.5 gigahertz. So it makes sense that to have a larger number of beams to cover those areas to exploit this beam forming. So that's a very good point. Yeah, thanks. Okay, so this single figure gives a different aspect like blocking and everything, blocking speed, how dense network can be, how the density of the network base stations affect the performance, and also how many beams one should have at the base station. So this is a downlink example, but this can also similar analysis can be done for uplink. But the uplink analysis will be much more challenging than downlink analysis. So since I'm running out of time, I will just briefly give the other way around. So how practice can lead to theories. I was talking about theory to practice until now. So in practice, what happened, I was talking about this beam switching problem, right? So the users have these panels, you have a phone, and then you have a front side of the phone and the back side of the phone. And as you're moving, the base station might lie on the front side of the phone and the next base station might lie on the back side of your phone. So this phone shows the side view of the phone. Let's say this X1 lies on this side and the next serving base station lies on this side. So there will be a beam switching, right? So it is important how frequently this beam switching happens. So this is a very practical problem that we were analyzing with Bell Labs, and that leads to a fundamental mathematical problem, which this problem can be transferred into mathematics, but this can be applied to a much whole general area, meaning that assuming that you are in a spacecraft which is moving in 3D and you are looking at one star, you are communicating with one planet, let's say at Earth, X1 is Earth and then X2 is Mars, and then you are traveling on this on spacecraft, and how to handle that situation of switching between the beams in that. So this is just a hypothetical case, but this could be a possible. So that is what the mathematics does, right? So giving some abstract results. So we can calculate some abstract, so we could do some fundamental results which were not existing in point process theory using this practical problem. So there is a possibility also doing those things just to motivate people that is not only theory is useful for the solving practical problems, but from practical problems, there could be some fundamental contributions in the mathematics just to give the motivation. Now to conclude this talk, I would like to give some summary. As we saw, essentially the system level analysis stochastic geometry for 5G NR can cover like different spectrum of this beam management aspect. Like essential scenario characteristics such as operational frequency, like whether you're operating sub-6 or millimeter wave, blockage characteristics, whether there is a line of sight communication or non-line of sight communication. Also the technological features such as the beamforming configuration, meaning that how many beams can be there, which also depends on the multiple antenna structure, signal processing characteristics, delay overheads due to the mobility, beam selection and beam reselection, network deployment choices, how dense network can be, whether if you are operating at sub-6 or the millimeter wave, what should be the intersite distances, what should be the carrier bandwidth because it affects the noise. Also the traffic pattern, whether the users consist of the pedestrians or the vehicles, or you are in the train or the bullet train or the flight, if you're talking about and so on. So that this analysis was the first attempt at taking into capturing these different aspects of this 5G NR to calculate the performance that a user can get in this network. So this model we use for the 5G network, but there are also, you can go for the Wi-Fi also, for example, Wi-Fi 6, which uses also beamformed. And this model allows us that one single figure showed that there are different existing trade-offs that is very difficult to analyze using the system level simulations, such as we have different network density, path loss, interference, signal overhead due to this beam. So essentially, I wanted to show that although many of you might be knowing beamforming and beam management, my goal of this talk was to show that they introduce this stochastic geometry as an effective tool to analyze the system level simulations or the system level analysis for these beam-based radio access networks, such as 5G. So essentially, just to show or to motivate people to connect academia and industry, because I worked in academia and industry as well. Usually, this is the process that overall process towards these any standards or the practical deployment of a system. You have real systems here. You make model and perform simulation. This comes under system level simulation. This comes under the real field experiments. But what we focus on this aspect where we model the systems, then where we have this PPP modeling of base station, beamforming model, blockage model, and also construct some approximate theories, which could be this probability of beam misalignment, average values of overheads, antenna gain, and then also the theoretical prediction. So we give this optimal number of beams to the industry, and they can now do this system level analysis and the practical. In fact, to highlight here that when we did this analysis and Nokia Bell Labs did their system level analysis, system level simulations, what we find the number of optimal beams that I showed in that figure, they were quite close. So meaning that although there were some approximation that we considered for the tractable analysis, but the area of the number of beams, number of beams to use was quite close to what they were observing in experiments. So it shows the effectiveness of this stochastic. And this is the last slide to show the future direction. Obviously, this is a very exciting area in beamforming. You can do a whole lot of things in this area, but I will show just how we can extend to like some specific scenarios. I focus on only one user per cell, but one can go for the multiple users per cell. also I focus on only single cell scenario, meaning that either macro cell or the small cell, but one can heterogeneous cell, multiple tiers of the network, so like macro cell alongside with the micro cell or the small cells as well. Also, the other user mobility patterns, such as the random waypoint model, the user is moving in zigzag pattern rather than a straight line. Then the reflections of the signals, meaning that we consider the blockages, but there could be a reflection of the signal due to the buildings and so on. And also the 3D effects of that. If you extend this word to 3D, there will be things to consider like elevation, beam azimuth, elevation, and so on. And also, we did some part of this, like comparing the simulation, theoretical results and prediction with the system level simulations. Okay, thank you. That's all from my side. If you have any questions, I will be happy to answer.
Hey, Dr. Sanket, this is Parthiban here. I have a question. So the number of beams that are required, especially in a millimeter wave scenarios, that's primarily dependent on the path loss factor, so wherein all your frequency components will come into picture, isn't it?
Yes, that's correct. Yeah.
Yeah. So considering that aspect, and your maximization problem is effectively trying to find out the maximum number of beams that are required based on the average spectral efficiency constraint, isn't it? So don't you see some kind of a contradiction here in terms of the effective number of beams that can be needed?
Yeah, so that's a good point. So here, what it means that effect when we talk about the average effect to ASC, spectral efficiency, is that you can have a user, so you generate a realization kind of, you have a set of users in an area. What you do, there is a transmission going on. And then you kind of talk about the typical user, meaning that, let me go back to this figure here, it will be easy. So we are only, even though I was talking about this typical user, but this user represents the average performance of all users in a network realization. So meaning that, so this user might be near to the base station, it could be far from the base station, the frequency, as you said, the mmWave, the number of beams might be different. So even when you take these different randomness into account, and when you average over all this randomness, and then what is the optimal number of beams, this is what it gives. But in real time, obviously, the situation is more fluid, meaning that for each user, the number of beams will be, optimal number of beams will be different. But that's a good point, and this is what this last work I showed in the conclusion does. The thing, when we have multiple users in this case, and then how it affects the number of beams, this is what we showed in this work. So is that what you are asking, or did it answer your question?
Yeah, something of that sort. So I mean, primarily my point was that, you know, the frequency of operation, which eventually defines the number of you know, frequencies that are required. You know, as you go to the higher frequencies, due to the path loss factors, probably you have to put in a narrow beams to cover the area. So as you go narrower and narrower, and the number of beams would definitely, you know, proportionally would increase. So that being the primary constraints which defines the number of beams, and I mean, compared to that, your maximization problem derives the number of beams based on a different parameter, which is the area of effective area spectral efficiency.
Right, yeah, but what you are saying is also captured into that, right? It means when I was saying that it takes into also account the different frequencies, meaning that will affect this, if you go for the optimization problem, that what you are saying, the number of beams will essentially affect what will be the signal strength and what will be the interference, right? And that will also dictate the what is the number of beams. So essentially what happened that, as I said earlier, this that comes under the SINR, like signal strength and the interference, and that this. So let's go with this flow chart kind of. You have the number of beams for a given frequency and the path loss that decides your signal strength, and that decides your interference. So essentially that determines your SINR, and that essentially determines your average spectral efficiency. So yeah, obviously means you're right, means if we go for this ASC, you are seeing this pattern, but if you go for some other metric, let's say you go for the some potential throughput, meaning that not this ergodic average, but you go with some other metric of the throughput, obviously this optimal number of bits will change. But to answer your questions, that it does take into account what is the operating frequency, because that affects the propagation attenuation and also in turn affects the signal strength and the interference, so which is captured by this area spectral efficiency. And this area of spectral efficiency is used by industry quite frequently. So the way I have defined here area spectral efficiency, this is a very popular metric and very useful metric.
Yeah, okay, thanks for the clarification.
Sanket, one question from me. So, you know, I'm assuming that this model for selection, beam selection is sort of, you know, applicable in general across all frequencies. You know, for example, what I'm saying is that a BTS may have multiple antennas, you know, and they might have the millimeter wave band at the same time 700 megahertz band also propagating from the same BTS, from different antennas. And the handset is quite capable of switching across frequencies. Most of the 5G handsets are capable of switching across bands. So there can be some overlaps of the beams, right? Beam of the 28 gigahertz might overlap with beam of 700 megahertz and so on. So is your model sort of can be generalizable across all these bands, given the you know, the beam strength and so on?
Yeah,
or am I missing something? I'm not. Yeah.
No, yeah, certainly. As I said earlier, like this can be, what you're saying is kind of comes under this heterogeneous networks, right? You have macro cell operating at 700 megahertz, and you have small cell operating at 28 gigahertz. And then what could happen, and their beams might overlap. Essentially, I'm not sure whether the one base station can can operate because between these two things at the same time. But if we have different frequencies, there will be no interference, essentially, right? One beam is operating at the 700 megahertz, and then one beam is operating at 58 gigahertz. So there will be no interference between those beams. Even though they overlap geographically, there will be no interference, right? Because they operate at the whole different frequencies. Does that answer your question?
That's fine. Yeah, that's fine.
Yeah, but it is possible. Yeah, means irrespective of the frequencies, but even let's say not 700 gigahertz, but even in 6 gigahertz or related frequencies, there could be a possibility that one can have a macro cell and so let's say 6 gigahertz and 3.5 gigahertz. There might be operation, but there might be a possibility that the user can make a switch from one network to the another network, or the one frequency to another frequency, but I think there will be no interference. But certainly such analysis can be done using these models.
Thank you.
A question from my end, Sanket. Could you move to 35th slide?
Yeah, sure. Let me do that. This one, right?
Yeah, here. This GSN is the side lobe probability, isn't it?
It's a side lobe gain. Yeah.
Side lobe gain. Yeah, side lobe gain of the same base station. Perhaps the neighboring, outside of the beam, rather than the antenna gain at the interfering base station. This does not concern the interfering base station. Am I correct?
No. So this is actually at the same base station, meaning that this is, let's say this is an interfering base station, one interfering base station. So what I am saying here, that there is a base station, let's say here, and it's that interfering base station is serving this user here, its own user, not the user of interest right? And so this beam main lobe is pointing this direction, and the rest of this direction, like 2 pi minus phi n, is served by the main lobe. And then if our user of interest falls in this direction anywhere in this cone, then that user will experience interference from this base station with this main lobe gain. If the user is lying on this direction somewhere, then the interference gain to that our user will be GSM. So that's what it means, this will.
Okay. Then for follow-up question is, currently, let's assume you have a base station with about 10 beams, right? And one of the beams is directly connecting it's connecting or communicating with the user equipment through one of the beams, right?
Right.
So the remaining 9 beams would have this particular beam as a side lobe. Am I correct?
Not like that. So this is, yeah, that's a good point. I should clarify that. I mean, this is corresponding to only one beam. Okay,
Yeah.
so yeah, so this is only one beam. It shows the main lobe of one beam, and this is the side lobe of the same beam. But there will be other beams also here. Yeah, for the same base station. Yeah.
Their side lobes will be interfering with this particular main lobe.
Yeah, so that's a very good point. Yeah, what happens here? There are two models that are popular even in industry and in academia. One is called, the one I have used here is the grid of beams. So this is what we are talking about. So there is a beam that is covering this Wi-Fi area. Okay, and then if we have 10 beams, meaning that each beam is covering 36 degree approximately, right? And then 36 degree, then as the user moves, so then the next beam will become active. But at a given time, since we are assuming that there is only one user per base station as of now, that one base station is per resource block, meaning that at a given time and at a given frequency, what will happen only that in this grid of beams, only this one beam is active at a time. And then, but now if we have the situation is whole lot different if you have multiple users. So this is what this is a kind of a work in progress that I have been working recently. Is that if we have multiple beams and then multiple users, then the other beams are also at the same base station, serving base station, also active, and then the user lying in this area will have, let's forget about this is not an interfering base station, this is a serving base station. Then the user lying in this area will experience interference from the side lobes of other people. But this is just a caveat that this is a whole different area and quite a challenging problem, because it depends on how to add up the interference, not only the intercell interference, that is what we considered here. This expression shows this intercell interference, but there will be now intracell interference as well due to this side lobe. And it's a very interesting problem, I can say that based on my initial findings. And it's if somebody wants to venture into that problem, you are welcome. It's a very interesting problem. There are a whole lot of a new area of trade-offs in this problem.
Very interesting. Thank you. Thank you.
Yeah, sure. Yeah, you're welcome.
Questions from other audience?
Hi, Sanket. This is So I had a quick and a curious question. So thank you very much for the wonderful talk. So just wanted to ask, since you have analyzed or you have looked at the data which has already been analyzed by Nokia Bell Labs, so I presume here that their analysis would be more like a data fitting, right? Looking at the past data to come up with the value of those overhead metrics, so on and so forth.
Yeah, kind of. So yeah, it has to do with a lot of 3GPP as well, because 3GPP has a set of parameters defined. And and then they do these simulations using those 3GPP standards. So it's no secret actually. It means everybody knows what is that data, and that usually the way, because Nokia Bell Labs also build their own base stations and deploy their own base stations. So they have this information. I don't know how they have found this data, but these are the values that I received from them. And usually even in Qualcomm, I hope that the values that usually people observe is in this range, because everybody follows these 3GPP standards and the guidelines to do this system level simulation. And yeah.
I wanted to know if you could put a number to the percentage mismatch which you have observed after you have used the stochastic geometry framework to come up with these overheads which you have calculated theoretically. So do you have a number in terms of percentage mismatch? And if you could provide some insights as to where this mismatch was maybe higher, so that could open up potential research areas for us to maybe probe in. Because this is such an interesting area.
Yeah, that's a very good question, Amrita. Yeah, so let me come back to this table here. I show. Essentially, if you see that, means there are certain approximations. So frequency is the typical one. The bandwidth is the same. The noise density. Now, in practice, what could happen is that the key overhead mismatch. So these numbers are the same. So these are the practical numbers: 23 millisecond and 43 millisecond. Now, the approximation comes from the model that we have used for deploying the base stations, meaning this Poisson point process. Because it's a totally random model, it assumes that that they are randomly deployed. But in practice, what could happen is that if you go to a crowded area, there will be a cluster of the hotspots or the base station. If you go to rural areas, the situation, even just farther away from the crowded area, there will be a different geography of this base station location. So to me, it looks like essentially when we have had these results initially, for example, in this case, it is 60. It says that at this point, one should use 64 beams, as far as I remember. And then the Nokia Bell Labs had about 48 to 50 beams. They have found that if you use this grid of beams model, the number is about that distance. So it's not sure that if you go to that number is now lies between this 32 and 64. Then, but the spectral, they had a different metric to analyze the throughput. So this is a effective area spectral efficiency. The metric they assume is the kind of the watt fraction of the users achieve a certain throughput, meaning that in 3GPP that they have the user should have a 10 Mbps throughput or 20 Mbps throughput. So to answer your question in summary, that although the metrics are different, but the model of throughput, they assume that the range of the region they assume for the number of optimal beams is about this region. So we say 64, but it could vary from 40 to 80 or something like that. So there is inaccuracy, but it gives that, okay, the main purpose is that if you have 64, they can, rather than focusing on, let's say, 8 beams or 10 beams or 15 beams, they can start let's say, directly at 30 beams or 20 beams, 40 beams or the 50 beams, or they can start at 60 beams and then adjust according to the performance they see. And the approximations, so there is certainly there is a inconsistency between the what theory and the practice is there. And the approximations that we assume is that the beam misalignment is one. The second is that this modeling of this network deployment. We use the Poisson model, but there could be more accurate modeling of the base station location. Also, third one is the blockages, the way how you model the blockages. So there are more advanced model, but the complicated model that can even model these blockages, line of sight or non-line of sight communication. And certainly there is a path loss model, which for the even mmWave, I assume that this is a relay model, but in mmWave there are more realistic model, or the Nakagami one is one, another one is the Russian model. So if we go with that, the optimal number of beams that one can find will be different than what we have observed here.
Thank you, Sanket.
Yeah.
This is Debrath here. So, sorry, wonderful talk. I attended the flag and some parts of it. Very interesting, very nicely presented. So I have only one question to understand your view or vision in the direction. In slide 52, you said that the internal antenna for the spectrum handover around 30 milliseconds or 40 milliseconds, like that, around that. So, but ultra reliable low latency is expecting 10 milliseconds and below. And above the phi layer, there is a MAC layer. The MAC medium access control layer has a scheduler, which also tracks and of the velocity of the vehicles. So do you think from system level point of view, because theoretically optimizations, delay reductions has been gone, but system takes its own time to hand over from MAC schedulers complexity to phi layer spectrum, then to fire another from if 32 by 32 MIMOs are there. So how you think it can be reduced? What are the challenges, research challenges?
Yeah, that's a very good question. Okay, so so these are the 3GPP number, but I think this is for 5G NR, where we, as you know, in 5G NR, it's decomposed into three broad area. One is this enhanced mobile broadband, other one is this massive connectivity, and the third one is the ultra reliable and low latency. There are areas, for example, if we go for the ultra reliable, low latency, as you were saying, scheduling and so on. So this is a kind of a different, the way base stations schedule the resources for the user will be different than what it does for these typical mobile broadband cases. So what I can say that without revealing much proprietary information is that there are techniques where you can, in 3GPP itself, where you can change the scheduling the way the users are scheduling. But now it comes to the mobility. Obviously, mobility is a big challenge for the ultra reliability, and especially for the low latency, given that you have this interruption between that. And so to say that sometimes it is possible if the user is very mobile, I don't know whether these numbers will be sustainable. The key challenge is that is to schedule the user as soon as faster, because you know what happens, we have the uplink and downlink, right? In 5G, they use this time division duplex. At the same time, downlink is going and uplink is also going down. And then usually the famous slot structure is that depending on what is the subcarrier spacing, meaning that what is the slot duration, whether you're operating in 2.5 millisecond slot or 5 millisecond slot or 10 millisecond slot. So it depends on the subcarrier spacing that is used, 15 kilohertz, 30 kilohertz, and so on. And so for this ultra reliable, one has to use a very small slot duration, so that means that one has to use the higher subcarrier spacing, could be 120 kilohertz and so on, where the slot is 0.25 millisecond, I suppose. And then in that case, that how you schedule the user depending on the downlink and uplink. So the 5G is very flexible. And then let's say you have 5 sub-slot in one frame to transmit a frame. Then out of them, how many can be assigned for the downlink depending on, so meaning that if there are 3 slots in which there will be only downlink communication, then the communication can be done very fast. Also, it depends on how many resources can be allocated. Now, when it comes to the mobility, I'm not exactly sure, to be frank, that how these numbers are valid for the ultra reliable, because the standards for the ultra reliable and low latency communication is different than this 5G NR. So these numbers are essentially for this enhanced mobile broadband communication. But when it comes to the ultra reliability, it is important that how the scheduling is done, and it is important to operate at a small slot level, which the 5G allows us to do. It allows this flexible allotment of the slot. And the second is the scheduling, how frequently the base, if the user gets the data and then, or the base station gets the data, how it frequently can schedule the user for reception or the transmission of the data. So it depends on that. So there are different scheduling policies to do that. Okay. Yeah.
So thank you, Sanket, for a wonderful talk. So appreciate your time and interest in participating in this Samvaad-Talk. Okay, on behalf of our Samvaad team and IIIT as a whole,